What if venturing into the cosmos meant facing dangers so extreme they could rewrite the very definition of survival? Space exploration has always symbolized the pinnacle of human ambition, a bold leap into the great unknown. But beyond the promise of discovery lies a reality far less forgiving, an arena where invisible radiation threatens to unravel our DNA, where isolation chips away at the human spirit, and where even the smallest error could spell catastrophe. This isn't just a story of triumphs among the stars. It's a journey riddled with hidden perils that push the limits of technology, resilience, and the human body itself. In this video, we're uncovering 20 of the most unexpected and dangerous challenges lurking in the darkness of space. From life-threatening hazards like equipment malfunctions and cosmic weather to ethical dilemmas and the risk of alien pathogens, these are challenges humanity must understand and overcome as we aspire to venture further into the universe. Stay with us to explore why conquering these dangers is not only vital for our survival, but for the future of space exploration itself. Now turning to one of the most formidable challenges of space exploration, radiation exposure. Once astronauts leave the protective bubble of Earth's atmosphere and magnetic field, they are immediately exposed to a relentless barrage of cosmic and solar radiation. Unlike on Earth, where the atmosphere acts as a shield, deep space is an environment where high-energy particles, traveling at nearly the speed of light, zip through the void. These particles, originating from the Sun or even distant stars, carry enough energy to penetrate spacecraft walls and, worse, human tissue. Over time, this exposure can damage the very building blocks of life, our DNA, increasing the risk of mutations, cancer, and other life-threatening conditions. Vital organs are not spared either, with radiation targeting sensitive areas like the brain, heart, and gastrointestinal system. Imagine the force of a solar flare, a sudden eruption of intense energy from the Sun, sending out a wave of radiation that could bombard astronauts in its path. Without Earth's magnetic field to deflect these particles, as it does so effectively for those of us on the ground, the consequences in space are dire. This radiation threat doesn't just strike in intense bursts. It is also ever present in the form of galactic cosmic rays, which are nearly impossible to escape in deep space and pose long-term health risks for anyone on extended missions beyond Earth's orbit. Understanding and mitigating this invisible yet incredibly potent danger is not just a technical challenge, it is an existential one for the future of human space travel. As this danger looms larger in deep space, how can we protect astronauts from these life-altering risks? Stay with us as we explore the complexities of shielding technologies and the ongoing fight to overcome the challenges of radiation mitigation in our next segment. Moving forward, tackling the mitigation of radiation exposure proves to be a daunting task for scientists and engineers. Shielding spacecraft from radiation sounds straightforward in theory, but in practice it is riddled with complexities. Traditional shielding methods, such as using dense materials like lead, could offer protection but come with significant drawbacks. Lead and similar materials are extremely heavy, and every additional pound of weight increases the cost and challenges of launching a spacecraft. Furthermore, they are not entirely effective against all types of harmful radiation, particularly the high-energy galactic cosmic rays that penetrate even the thickest barriers. Researchers are exploring innovative alternatives, such as using hydrogen-rich materials, which have shown promise in blocking radiation. Water, for example, contains hydrogen and could serve a dual purpose as both a radiation shield and a life support resource. However, storing enough water to provide adequate protection adds logistical hurdles in terms of volume and weight. Another cutting-edge idea involves artificial magnetic fields designed to mimic the Earth's natural deflection of charged particles. These magnetic fields could theoretically create a protective bubble around a spacecraft, diverting radiation away from its interior. but the technology is still in its infancy, requiring immense power and posing challenges in maintaining stability over long durations. Even advanced materials like lightweight composites infused with radiation-absorbing properties have their limitations, as they cannot eliminate exposure entirely. The pursuit of effective shielding is further complicated by the need to balance protection with functionality, ensuring that spacecraft remain light enough for efficiency but robust enough to safeguard human lives. As technology stands today, no singular solution offers complete protection, making it clear that a multifaceted approach is essential. Combining innovative materials, strategic spacecraft designs, and artificial magnetic field technology could hold the key, but we are still years, if not decades, away from fully mastering these solutions. The fight against radiation exposure remains an ongoing battle, one critical to the success of prolonged human missions in deep space. As we address this challenge, another equally profound impact of space exploration comes into focus: the effects of microgravity on the human body. As the next challenge unfolds, the impact of prolonged microgravity on the human body emerges as a formidable hurdle in space exploration. In the microgravity environment of space, the absence of Earth's gravitational pull dramatically alters the way the human body functions. One of the most significant consequences is muscle atrophy. Without the need to counteract gravity, astronauts' muscles are underutilized, which leads to a gradual weakening and shrinking over time. Even with rigorous exercise routines aboard spacecraft, it is challenging to replicate the intensity and frequency of physical activity experienced on Earth. Similarly, the lack of gravitational force takes a toll on bone density. Astronauts lose calcium from their bones at a much faster rate, making them brittle and more prone to fractures. This phenomenon, known as spaceflight osteopenia, mirrors severe cases of osteoporosis back on Earth, but it occurs at an accelerated pace for those in space. The cardiovascular system also faces significant challenges. On Earth, gravity helps distribute blood throughout the body, but in microgravity, fluids shift upwards, causing facial puffiness and increased pressure on the head. Over time, the heart, which does not have to work as hard to pump blood in this environment, can weaken, a condition that raises concerns about long-term cardiovascular health. The experiences of astronauts on extended missions aboard the International Space Station vividly highlight these challenges. For example, crew members returning to Earth often require weeks or even months of physical rehabilitation to regain muscle strength, bone density, and cardiovascular fitness. One astronaut reported difficulties walking and standing unassisted immediately after landing, illustrating the profound adjustments the body undergoes after an extended period in space. These biological changes are not just short-term inconveniences. They pose serious risks for future missions, especially those venturing into deep space, where years rather than months might be spent in microgravity. Prolonged exposure to such an environment could potentially lead to irreversible damage, jeopardizing both the health of the crew and the success of the mission. As these challenges come to light, it becomes clear that a deep understanding of microgravity's effects is essential to developing strategies that will protect astronauts during and after their journeys. This brings into focus yet another layer of complexity, examining the long-term health concerns that persist even after returning to Earth. Now turning to the long-term health concerns stemming from microgravity, the journey does not simply end when astronauts return to Earth. Many of the changes their bodies undergo in space persist long after re-entry, presenting new challenges for rehabilitation and life back home. One of the most concerning effects is impaired vision. Prolonged fluid shifts during space missions increase pressure inside the skull, pressing against the optic nerve and causing what is known as spaceflight-associated neuroocular syndrome. This condition has led to blurred vision and structural changes in the eye, with some astronauts experiencing permanent visual impairment. Additionally, the immune system, already stressed by the unique environment of space, becomes weakened over time. This leaves astronauts more susceptible to infections and illnesses, both in space and post-mission, as their bodies struggle to readjust to Earth's natural microbial exposure. The immune system may even become less effective at identifying and eliminating harmful pathogens, a risk that only grows with longer durations in space. Rehabilitation after extended space flights is another significant hurdle. Astronauts often report difficulties performing simple tasks like walking or standing due to the severe reconditioning their muscles and bones have undergone. This recovery process can take months, and in some cases, full pre-mission capabilities might never be fully regained. For astronauts who venture on future missions lasting years, such as those to Mars or beyond, these effects could be even more severe and long-lasting, potentially compromising their ability to carry out mission-critical tasks upon arrival or once they return to Earth. These examples underscore the pressing need for advanced strategies to mitigate the long-term health concerns of microgravity. The road to deep space exploration demands not only the prevention of these conditions, but also improved methods to reverse or manage them afterward. With these lingering challenges in mind, the psychological toll of space exploration emerges as another critical layer worth exploring. As the next challenge unfolds, the psychological toll of space exploration reveals itself as a profound and often underestimated danger. Isolation from family, friends, and the familiar comforts of life on Earth weighs heavily on the mental well-being of astronauts. Spending weeks, months, or even years in the confined spaces of a spacecraft or space station can lead to feelings of loneliness and disconnection. The absence of real-time conversations due to communication delays with Earth only amplifies this sense of detachment, reinforcing the emotional strain. Furthermore, the confined environment itself presents an ongoing challenge. Living and working in close quarters with the same small group of people can create tension, misunderstandings, and even conflict. The lack of personal space, combined with the high stakes of mission objectives, can escalate minor disagreements into significant interpersonal challenges. These dynamics are further complicated by the pressure to maintain composure and professionalism despite the emotional hardships astronauts face. Another key factor is the sheer distance from Earth. Knowing that immediate help or rescue is impossible can create a heightened sense of vulnerability and anxiety. This distance also imparts an eerie sense of finality. There is no escape hatch from the mental and emotional trials posed by deep space. Over time, these psychological challenges can manifest as depression, chronic stress, or impaired decision-making, which could jeopardize not only the individual astronaut but the success of the mission as a whole. These mental health risks highlight the need for strategies that address the unique emotional demands of space exploration. As we uncover these psychological struggles, it becomes crucial to explore the mechanisms designed to help astronauts cope with the challenges they face. Moving forward, let us delve into the coping mechanisms employed by space agencies to address the mental health challenges faced by astronauts. Recognizing the profound psychological toll of space exploration, organizations like NASA have developed innovative strategies to help astronauts maintain their emotional well-being during missions. One such approach is the use of virtual reality tools designed to simulate calming and familiar environments from Earth. By immersing astronauts in digital recreations of forests, beaches, or even their hometowns, these experiences aim to reduce feelings of isolation and provide a brief mental escape from the confines of a spacecraft. Recreational activities also play a critical role in promoting mental health. Astronauts are encouraged to engage in exercise routines, watch movies, read books, or even play musical instruments, allowing them to unwind and manage stress effectively. These seemingly small moments of leisure can create a necessary balance between intense work demands and personal downtime. Telecommunication with family and friends remains another cornerstone of emotional support. Regularly scheduled video calls or recorded messages help astronauts stay connected with their loved ones, reminding them of the life waiting for them back on Earth. However, as valuable as these measures are, their limitations become starkly evident in the context of extended missions, such as those envisioning travel to Mars. With communication delays of up to 20 minutes each way, real-time interaction becomes impossible, potentially heightening feelings of isolation. Furthermore, the psychological impact of knowing that return to Earth might take years, or that immediate rescue during a crisis is not feasible, places an unparalleled strain on astronauts far beyond what current coping mechanisms can fully address. These challenges underscore the need for continuous innovation in mental health support systems as humanity prepares for missions of unprecedented duration and distance. With these hurdles in mind, the question of physical risks in space becomes our next focus as we examine the threats posed by the growing problem of space debris. Now turning to the looming threat of space debris, we confront a hazard that grows with every launch into orbit. Surrounding our planet are millions of fragments, ranging from defunct satellites and spent rocket stages to stray bolts and paint flecks, each traveling at extraordinary speeds that amplify their destructive potential. Even an object as small as a paint chip can cause significant damage when colliding with a spacecraft, given the immense velocity at which both move. Over the years, there have been numerous incidents that demonstrate just how precarious the situation is. For example, the satellite Cosmos 1934 collided with the communication satellite Iridium 33 in 2009, creating an enormous cloud of debris that continues to orbit Earth to this day. Such collisions not only destroy expensive equipment but also add to the growing junkyard of debris, increasing the risk for all future missions. This brings us to the alarming prospect of the Kessler syndrome, a theoretical scenario where a single collision sets off a cascading chain reaction, generating an ever-expanding field of space debris. The implications of this phenomenon are grave. Should it occur, it could render some orbital regions entirely unusable for decades, if not centuries, severely limiting humanity's ability to use satellites for communication, navigation, and research. The reality is that every launch and every operation in space adds to this problem, and without effective measures to manage debris, the risks will only continue to escalate. With this critical issue in mind, solving the challenges of space debris management becomes imperative, leading us to explore the complexities of addressing this ever-present danger. As the next challenge unfolds, addressing the space debris problem proves to be as complex as it is critical. One promising idea is the development of deorbiting devices specifically designed to remove derelict satellites and other large debris from orbit. These technologies include nets, harpoons, and robotic arms that can capture debris and guide it to a controlled re-entry over uninhabited areas of Earth. While innovative, these devices face significant obstacles such as the high cost of deployment, technical difficulties in tracking and capturing fast-moving debris, and the risk of unintended collisions during such operations. Another proposed solution is the use of cleaning satellites, sometimes referred to as space janitors, which would actively seek out and neutralize dangerous debris. Yet, this approach introduces its own set of challenges, including the sheer number of objects to be dealt with and the considerable resources required to maintain such a fleet. Beyond technological efforts, international cooperation plays a vital role. Creating and enforcing global regulations to mitigate debris generation and promote responsibility among spacefaring nations is essential. This includes limiting the lifespan of satellites, requiring safe-to-orbit plans for spent equipment, and establishing penalties for non-compliance. However, achieving consensus among countries with differing priorities and technological capabilities is far from straightforward. The financial burden of implementing these solutions is another significant hurdle. Developing and deploying debris removal technology alongside crafting and enforcing international agreements demands substantial investment. In a field where funding is often allocated to more immediate needs, finding the resources to tackle a long-term issue like debris management remains a persistent challenge. Despite these difficulties, the urgency of the situation cannot be overstated. Failing to address the growing threat of space debris could jeopardize the future of space exploration and the countless benefits humanity derives from satellite technology. This high-stakes dilemma underscores the need for innovative, collaborative, and proactive measures, a theme that echoes across other hazards in space exploration, including the critical risk of equipment failure, which we now turn to next. Now turning to the critical risk of equipment failure, the stakes in space are extraordinarily high when technology does not perform as expected. Imagine being millions of miles away from Earth, relying entirely on machinery to sustain life, navigate, and communicate, only to face a malfunction. One of the most famous examples of this occurred during the Apollo 13 mission, when an oxygen tank explosion turned what was meant to be a lunar landing into a desperate fight for survival. The explosion not only crippled the spacecraft service module, but also resulted in a cascading series of failures, forcing the crew and ground control to come up with innovative solutions in real time. The astronauts used the lunar module as a lifeboat, rationing limited resources while engineers on Earth devised ways to adapt existing tools and systems to an entirely new purpose. This near-tragedy highlights how even a single fault in equipment can snowball into a life-threatening crisis in the unforgiving environment of space. Beyond historical examples, modern missions continue to grapple with the potential for unforeseen malfunctions. Spacecraft are often subjected to extreme conditions, from intense radiation to drastic temperature fluctuations, all of which can degrade components over time. Even microscopic flaws in design or manufacturing can lead to disastrous outcomes when stressed by space's harsh realities. The challenge lies in the fact that fixing broken equipment in space is not like replacing a part in your car or calling a technician to repair a malfunctioning device. Astronauts must diagnose and address issues using only the tools and spare parts available on board, often under significant time pressure. For instance, during the Hubble Space Telescope's servicing missions, astronauts repeatedly performed intricate repairs in zero gravity to restore and enhance its functionality. Each procedure required flawless execution, as even the smallest mistake could have rendered the telescope useless. The lessons from these missions emphasize the importance of building systems with redundancy, rigorous testing, and adaptability. However, despite countless advancements in technology, the risk of equipment failure remains an ever-present danger, demanding constant vigilance and innovation from engineers and astronauts alike. This unavoidable hazard underscores the need for thorough preparation and robust contingency planning, a reality that extends into yet another layer of this complex puzzle: the inherent risks that come with making quick improvisations in the face of such emergencies. As the next challenge unfolds, the risks of improvisation in space emergencies come into sharp focus. While ingenuity and quick thinking have saved countless missions, relying on makeshift fixes introduces an entirely new layer of uncertainty. Astronauts often face situations where standard procedures simply do not apply, forcing them to create ad hoc solutions with limited resources. Each decision carries immense weight, as the smallest miscalculation could make the situation far worse. Take, for instance, the carbon dioxide crisis aboard Apollo 13. When rising levels of the toxic gas threatened to suffocate the crew, engineers on Earth devised a way to fit a square peg into a round hole, literally. Using only materials available on the spacecraft, such as duct tape, plastic bags, and the covers of flight manuals, the astronauts assembled a contraption to filter the air. This ingenious fix worked, but it underscores just how precarious the situation had become. Improvisation, while often necessary, is inherently risky. Space, with its zero room for error, magnifies these risks exponentially. A solution that works temporarily might fail under prolonged stress or cause unforeseen issues elsewhere in the system. Furthermore, the high-stakes environment can push astronauts to work under extreme physical and mental fatigue, leaving them vulnerable to mistakes. Even with the most rigorous training, it is impossible to prepare for every conceivable scenario, meaning improvisation often operates in the realm of the unknown. Compounding this challenge is the fact that space equipment is not inherently designed for on-the-spot modifications. Components are meticulously optimized for specific tasks, making them less adaptable to situations they were never intended to handle. This rigidity forces astronauts to innovate in ways that constrain the limits of both their tools and their ingenuity. For example, during a spacewalk to repair the International Space Station's cooling system in 2010, astronauts encountered unexpected complications that required real-time adjustments to their plan. They succeeded, but only after hours of improvisation that could have easily gone awry. All of this illustrates why, even with highly reliable technology and extensive testing, the unpredictability of space exploration ensures that risks can never be entirely eliminated. The need for improvisation will always exist, yet it remains a gamble that carries the weight of life and death consequences. Moving forward, this sobering reality brings us to another critical frontier: the challenges of providing sustainable food and water for long-term space travel, an issue that goes far beyond just packing extra supplies. Now turning to the challenges of producing and storing food and water in space, it becomes clear that sustaining life beyond Earth is far more complex than it may initially seem. Astronauts cannot simply pack enough food and water for long missions, as storage capacity, weight limitations, and the deterioration of supplies over time pose significant hurdles. Stored food in space faces a unique problem: nutrient degradation. Over months and years, essential vitamins and minerals in packaged meals begin to break down, potentially leaving astronauts without the nutrition needed to stay healthy. Furthermore, the process of storing food for extended periods in a zero-gravity environment often alters taste, texture, and even the structural integrity of the food itself, making meals less appealing and less effective as a source of energy and morale. Water, on the other hand, presents its own set of challenges. Unlike on Earth, where water is abundant and easily replenished, astronauts must rely on tightly controlled recycling systems to collect, purify, and reuse every drop. These systems, while innovative, are not foolproof. Any failure in the system could lead to a critical shortage, as there are no natural sources to draw from in space. Additionally, maintaining these systems requires constant monitoring and upkeep, adding yet another layer of complexity to deep space missions. The combination of limited resources, space constraints, and the harsh environment of space creates immense logistical difficulties in creating sustainable life support systems. These challenges are amplified in long-term missions, such as a journey to Mars, where the time and distance involved would far exceed any mission humanity has ever undertaken. Addressing these food and water limitations is not just a technical issue but a matter of survival, one that will demand unprecedented innovation and collaboration as humanity ventures further into the cosmos. With the next phase of this exploration in sight, the conversation shifts to potential solutions and their inherent shortcomings in making space survival truly viable in the face of such overwhelming obstacles. Moving forward, potential solutions to overcome the daunting challenges of food and water in space are being explored with incredible ingenuity. One promising approach is hydroponic farming, where plants are grown without soil, using nutrient-rich water solutions instead. This method allows for efficient use of limited resources, providing astronauts with fresh produce and a much-needed psychological boost. Imagine the simple joy of eating a crisp, freshly grown vegetable after months of packaged meals, a luxury that hydroponics could offer. However, while hydroponic systems show great promise, they are far from perfect. They require significant space, energy, and constant management to ensure the delicate balance of water, light, and nutrients, all of which are particularly difficult to maintain in a zero-gravity environment. Equipment malfunctions or system contamination could lead to a loss of crops and therefore a critical food shortage. When it comes to water, recycling systems have been a game changer for space missions. These systems are designed to capture and purify everything from humidity in the air to wastewater, transforming it into drinkable water. The idea is simple, not a single drop is wasted. Yet, these systems, while highly innovative, are extremely complex and prone to wear and tear over time. Any failure could lead to catastrophic consequences, as water is not only essential for drinking, but also for food preparation and daily hygiene. Furthermore, such systems require substantial energy to operate, posing additional challenges for missions with limited power supplies. Meal replacements such as compact, nutrient-dense bars or freeze-dried meals offer another potential solution. They are lightweight, easy to transport, and have long shelf lives. However, relying exclusively on these options over extended periods could have negative impacts on both physical and mental health. The lack of variety and fresh ingredients often leads to something known as menu fatigue, where astronauts find it increasingly difficult to consume the same types of meals repeatedly, leading to reduced calorie intake and nutritional deficiencies. Each of these solutions, while revolutionary in its own right, highlights a recurring theme. They are not yet fully equipped to meet the demands of long-term space exploration. Whether it is the fragility of hydroponic systems, the energy-intensive nature of water recycling, or the limitations of meal replacements, these approaches each carry shortcomings that must be addressed before humanity can boldly venture into deep space. And as we delve into the vast unknown, these technical hurdles are only part of the equation. The next hidden danger takes us into uncharted biological territory, the potential risk of alien pathogens. As the next challenge unfolds, we step into a realm that feels like science fiction, but is rooted in very real scientific concerns, the risk of alien pathogens. When astronauts explore other planets, asteroids, or moons, they might unknowingly come into contact with microorganisms that are completely foreign to Earth's biology. These extraterrestrial microbes, if they exist, could pose risks upon returning to Earth. Imagine the implications of introducing an unknown pathogen into our biosphere. Would it be harmless, or could it evolve unpredictably, potentially impacting human health or even entire ecosystems? Unfortunately, because we have no prior experience with alien microorganisms, the risks are largely theoretical but no less concerning. To address this danger, strict biosecurity measures are enforced during space missions. For instance, samples brought back from missions are subjected to rigorous quarantine protocols to ensure that they pose no threat before they are studied further. This was seen during the Apollo missions, where lunar samples were sealed and astronauts were quarantined for weeks upon their return. However, as our ambitions extend beyond the Moon to places like Mars or the icy moons of Jupiter, the complexity of these precautions must be scaled up significantly. A single oversight in handling extraterrestrial material could have far-reaching consequences. Adding to the challenge is our limited understanding of alien life forms. If life exists elsewhere, it could be fundamentally different from what we know, potentially eluding our detection methods or behaving in ways we cannot predict. This lack of familiarity makes the threat both elusive and alarming. While the chance of encountering harmful alien pathogens may seem slim, the stakes are too high to take lightly. And as we consider the possibility of extraterrestrial life impacting Earth, we must also examine the flip side of this equation, how humanity itself could contaminate pristine alien environments. Now turning to the flip side of the equation, we explore the risk of humanity contaminating pristine alien environments. As we venture deeper into space, every spacecraft, rover, or astronaut carries with them the potential to introduce Earth-based microbes to other worlds. Despite rigorous sterilization processes, it is nearly impossible to eliminate all microbial life from our equipment, given how resilient certain organisms can be. For example, extremophiles microorganisms that thrive in extreme conditions have shown an uncanny ability to survive environments like those found in outer space. If such microbes were to hitch a ride on our missions, they could potentially establish themselves in alien ecosystems, assuming the conditions are even slightly favorable. This raises serious concerns about the unintended consequences of contaminating other planets or moons, particularly ones where life may exist or could potentially develop in the future. Not only would this undermine the scientific integrity of our search for extraterrestrial life by creating false positives, but it could also disrupt natural processes on these celestial bodies in ways we cannot yet foresee. Imagine the scenario of microbial contamination on Mars, where scientists are eager to determine whether life ever existed or still exists beneath its surface. If we unknowingly introduce Earth microbes, distinguishing between native Martian life and contaminants could become an impossible task, jeopardizing the core purpose of exploration. The same applies to icy moons like Europa or Enceladus, which are characterized by their subsurface oceans. These environments are considered some of the most promising places to search for extraterrestrial life, yet they are extremely vulnerable to contamination. To address this, international treaties and planetary protection policies have been established, including the Outer Space Treaty, which obligates nations to avoid harmful contamination of space and celestial bodies. However, as space exploration intensifies and commercial entities join the race, ensuring compliance with such protocols becomes increasingly challenging. The ethical responsibility to preserve the natural state of other worlds is one we must uphold, not only for the sake of scientific discovery, but also for the long-term sustainability of space exploration. As we proceed into this uncharted frontier, the imperative to balance human ambition with the respect for alien ecosystems becomes clearer. While the risk of contamination forces us to think critically about the footprint we leave behind, it also underscores the need for collaborative efforts and advanced technologies to mitigate these dangers. And as we weigh these ethical and scientific considerations, another critical challenge comes into focus: how limited medical support in space could turn even minor health issues into life-threatening crises. Moving forward, we examine the formidable challenge of dealing with medical emergencies in the vast expanse of space, where comprehensive medical facilities are non-existent. In the isolated, hostile environment of space, even a minor injury can escalate into a life-threatening situation. Consider the risks astronauts face during spacewalks, for example. One misstep or equipment failure could lead to abrasions, fractures, or other physical injuries. Without immediate access to a fully equipped medical facility, addressing these issues becomes a daunting task. Beyond external injuries, the specter of internal ailments like appendicitis or kidney stones looms large. These conditions, which on Earth could be treated relatively quickly with surgery or other interventions, become incredibly dangerous when millions of miles away from the nearest hospital. The zero-gravity environment further complicates matters, as it affects the way blood flows, how wounds heal, and even how medications work. Imagine the challenge of performing complex medical procedures like surgery without the ability to stabilize instruments or prevent bodily fluids from floating away. Current spacecraft and space stations are equipped with basic medical kits and medications, but these resources are limited to treating only the most common or minor issues. In the event of a serious medical complication, the options become grim. The affected astronaut may need to be stabilized and sent back to Earth, a process that could take days or even weeks depending on the mission's distance. This delay could prove fatal for conditions requiring urgent intervention. Furthermore, the lack of a trained surgeon on board most missions adds another layer of risk, as crew members are typically only trained in first aid and basic medical procedures. This stark reality underscores an urgent need for advanced medical technologies tailored for space. Efforts are underway to develop innovative solutions such as compact diagnostic tools, robotic surgery systems, and telemedicine platforms that allow Earth-based specialists to guide procedures remotely. However, these technologies are still in their infancy and have yet to be thoroughly tested in the harsh realities of space. Until then, the danger of limited medical support remains a sobering reminder of how unprepared we are to handle the unpredictable challenges of long-term space exploration. As the quest for safer space travel continues, these limitations highlight an area demanding immediate focus and innovation. And yet, while the absence of robust medical care in space presents a significant hurdle, it is not the only logistical obstacle. The challenge of managing fuel shortages during deep space missions poses another critical risk to the safety and success of space exploration efforts. Now turning to the technological strides aimed at addressing the limitations of medical support in space, researchers and space agencies are exploring groundbreaking innovations. Compact diagnostic tools, for instance, are being designed to rapidly assess an astronaut's condition with minimal equipment. These devices could potentially detect infections, monitor vital signs, and even identify serious conditions like internal bleeding. Such innovations hold promise, but they are still far from being foolproof. Current prototypes require further testing to ensure they can function reliably in the harsh microgravity environment of space. Telemedicine, another promising avenue, allows Earth-based specialists to guide astronauts through complex medical procedures in real time. While this technology has seen success in remote locations on Earth, implementing it in space introduces significant challenges. Communication delays, which can range from seconds to over 20 minutes depending on the mission's distance from Earth, make real-time guidance difficult during emergencies. Furthermore, the unpredictable nature of space missions can result in periods of complete communication blackout, rendering this approach unreliable in critical moments. Another key area of development is robotic surgery systems, which aim to perform precise medical procedures autonomously or with minimal human intervention. These systems could potentially handle operations ranging from stitching wounds to performing surgeries like appendectomies. However, the current models are bulky and require a stable environment to operate, making them impractical for space missions as of now. Additionally, these robots rely heavily on advanced programming and real-time monitoring, which could falter under the technical and environmental constraints of space travel. To address these gaps, researchers are also experimenting with advanced medical training programs for astronauts, incorporating virtual reality simulations that mimic various emergency scenarios. While these programs enhance an astronaut's ability to handle injuries or illnesses, they cannot replace the expertise of a fully trained surgeon. The reality remains that medical innovations for space exploration, though promising, are still in their infancy. They are not yet reliable enough to guarantee the safety of astronauts facing life-threatening medical emergencies millions of miles away from Earth. These limitations highlight not only the complexity of the problem, but also the urgency to accelerate research and development in this field. As we strive to make human exploration of space safer, the quest for dependable medical technologies represents one of the most pressing challenges. This need for technological breakthroughs is a recurring theme in space exploration, and it becomes particularly evident when considering the critical risk of running out of fuel during extended missions. As the next challenge unfolds, we face the critical threat of fuel shortages during space missions, a danger that could leave astronauts stranded in the vast and unforgiving expanse of space. Fuel is not just a resource for propulsion. It is the lifeline that ensures a spacecraft can navigate, maneuver, and ultimately return safely to Earth. A miscalculation, unexpected detour, or malfunction can quickly deplete reserves, leaving little to no margin for error. Real-life incidents such as the fuel concerns during the Apollo missions underscore just how precarious these situations can become. For example, during the historic Apollo 13 mission, a catastrophic failure in an oxygen tank forced the crew to improvise their course back to Earth. While the immediate crisis was not solely about fuel, the mission highlighted how razor-thin margins in space can escalate into life-threatening dilemmas. Another instance occurred with the Apollo 11 moon landing, where the lunar module's descent was marked by dwindling fuel levels. Astronauts Neil Armstrong and Buzz Aldrin had only about 30 seconds of fuel remaining when they successfully touched down. Such narrow escapes emphasize the ever-present risk of running out of fuel in scenarios where precision and timing are paramount. Unlike on Earth, where refueling is a relatively simple process, space offers no such convenience. The lack of refueling infrastructure in orbit or on other celestial bodies means that every mission must plan and carry sufficient fuel, accounting for every possible contingency. However, the heavier the fuel load, the more energy is required to launch and propel the spacecraft, creating a paradox that engineers continuously wrestle with. In the harsh reality of space exploration, even the best calculations cannot account for every unknown variable, making fuel shortages an urgent and potentially catastrophic issue. This challenge underscores the need for innovative solutions, a topic we will explore in depth as we move forward. Moving forward, we delve into potential solutions to the pressing issue of fuel shortages, exploring how advancements in propulsion technologies could redefine the future of space travel. One such innovation is the ion thruster. Unlike conventional engines that rely on chemical fuel, ion thrusters use electricity to accelerate ions, producing a steady and efficient propulsion system. These systems require far less fuel compared to traditional methods and have already proven their reliability in missions like the Dawn spacecraft, which explored the asteroid belt. However, ion thrusters produce relatively low thrust, making them unsuitable for rapid maneuvers or escaping the gravity of large planets. This limitation means they are best suited for long-duration missions where efficiency outweighs speed. Another promising technology is nuclear propulsion, which involves using nuclear reactions to generate immense energy. This approach holds the potential to drastically reduce travel times, opening doors to faster journeys to Mars or even further into deep space. That said, nuclear propulsion comes with its own set of challenges, including safety concerns and the need to perfect complex designs that remain largely untested in real-world conditions. Solar sails, on the other hand, offer a completely different approach. These large, reflective surfaces harness the power of sunlight to propel spacecraft without requiring fuel. While this technology eliminates the need for heavy fuel loads, it is highly dependent on the proximity to the sun and cannot provide the propulsion needed for intricate maneuvers or missions to darker, outer regions of the solar system. These innovative systems highlight humanity's pursuit of sustainable and efficient ways to explore the cosmos, yet they also introduce new risks. Technological failures, unproven designs, and the uncertainty of relying on relatively new advancements mean that these solutions are not yet foolproof. As we continue to innovate, the balance between reducing fuel concerns and ensuring reliability remains a critical challenge. The next chapter of our exploration brings us to another unpredictable force that space travelers must contend with: the dangers of space weather. As the next challenge unfolds, we enter the volatile realm of space weather, a force as unpredictable as it is dangerous. Solar flares, for instance, are immense bursts of radiation that erupt from the sun's surface, sending waves of highly charged particles hurtling through space. While Earth's magnetic field shields us from the majority of these particles, astronauts in deep space or on missions to the Moon or Mars are exposed to their full impact. A single powerful solar flare could disrupt critical spacecraft systems, interfere with communication channels, and even pose life-threatening health risks to the crew by delivering a sudden dose of intense radiation. But solar flares are only one part of the puzzle. Cosmic rays, which are high-energy particles originating from outside our solar system, relentlessly bombard anything in their path. Over time, exposure to these rays can cause severe damage to both human tissue and electronic equipment, gradually weakening spacecraft components and increasing the risk of system failures. Adding to this complexity are geomagnetic storms, which occur when solar wind interacts with Earth's magnetic field. These storms can wreak havoc on satellites orbiting the planet, disrupting navigation systems, power grids, and communication networks. In deep space, the effects of such storms are even more severe, as there is no protective magnetic field to buffer their impact. The unpredictable nature of space weather makes it a formidable challenge, as these events can occur with little to no warning. Despite efforts to monitor solar activity and predict cosmic phenomena, our ability to forecast space weather remains limited, leaving astronauts and their missions vulnerable to these immense forces of nature. With such high stakes, understanding and addressing the dangers of space weather is essential as we push further into the cosmos. Moving forward, we turn our attention to an equally pressing concern for space explorers: the psychological and logistical challenges posed by the isolation from Earth. Now turning to the critical task of predicting these cosmic threats, we face a significant challenge: the inherent unpredictability of space weather. Despite advancements in technology, forecasting solar flares, cosmic rays, and geomagnetic storms remains an imperfect science. Solar activity, for example, follows an 11-year cycle, but pinpointing when a flare will erupt or how intense it will be is still a daunting task. Space agencies around the world, including NASA and the European Space Agency, are investing heavily in research to enhance our understanding. Sophisticated solar observatories and spacecraft, such as the Parker Solar Probe, are being utilized to study the Sun up close, gathering detailed data on solar winds, magnetic fields, and plasma eruptions. These missions aim to improve the accuracy of our predictions and provide earlier warnings of solar events. Additionally, efforts are underway to monitor cosmic rays more effectively. Instruments like the Alpha Magnetic Spectrometer aboard the International Space Station are helping scientists map and analyze these high-energy particles in greater detail. Despite these efforts, our forecasting abilities are still limited by the sheer complexity of space phenomena. Unlike terrestrial weather, which we can observe and analyze with vast networks of sensors, space weather operates on such enormous scales and at such high speeds that even small errors in prediction can lead to devastating consequences. Developing more reliable early warning systems is not just a scientific pursuit but a necessity for the safety of future space missions. These systems must be capable of detecting solar activity and cosmic rays in near real time and providing actionable insights for mission planners and crews. As we continue to push for breakthroughs in this area, we must also prepare for the reality that some events may remain beyond our ability to predict. This sobering truth underscores the importance of resilient spacecraft designs and contingency planning. With the next phase of the journey in sight, we now turn to another profound obstacle for spacefarers: the psychological and logistical challenges of enduring isolation from Earth. With the next phase of the journey in sight, we delve into one of the most profound challenges of space exploration: the isolation from Earth. Imagine being millions of miles away from the only home you have ever known, with no way to return quickly if something goes wrong. For astronauts venturing deep into space, the psychological and logistical hurdles of this separation are immense. One of the first and most pressing issues is the delay in communication. Unlike the near instantaneous contact we enjoy on Earth, messages sent between a spacecraft and mission control can take several minutes, or even up to 40 minutes round trip on a Mars mission, due to the vast distances involved. This delay can make real-time problem-solving nearly impossible, forcing crews to operate with unprecedented levels of independence. Beyond the technical challenges, there is the emotional toll of being completely cut off from loved ones for months or even years at a time. Astronauts must cope with the weight of knowing that, should an emergency arise at home, they are powerless to offer immediate support or even receive it themselves. This can lead to feelings of helplessness, guilt, and profound loneliness. Additionally, the lack of familiar sights, sounds, and comforts from Earth can add to the sense of isolation, exacerbating stress, anxiety, and even depression. In these moments, the weight of being so far removed from the safety of Earth becomes a psychological test of endurance. Logistically, isolation also presents a critical problem: the inability to receive immediate help. On Earth, rescuers, medical teams, and supplies can be mobilized quickly in a crisis. In deep space, however, astronauts must rely entirely on the resources and knowledge available on their spacecraft. A malfunction, injury, or unexpected challenge could pose life-threatening risks, with no immediate way to send assistance. As space agencies prepare for missions to Mars and beyond, the psychological and logistical challenges of isolation necessitate innovative solutions. Technologies to facilitate delayed but meaningful communication, methods for fostering mental well-being, and advanced self-sufficient systems for medical and operational emergencies are all areas of intense research. However, even with these advances, the profound reality of being so far from Earth will remain an ever-present challenge for space explorers. Moving forward, we examine how these challenges become amplified in missions to destinations like Mars, where the distance from Earth stretches human resilience and ingenuity to its limits. Moving forward, let us consider Mars missions as a lens through which to view the intensification of isolation challenges in deep space exploration. A journey to Mars represents a monumental leap, with missions likely spanning 2 to 3 years, including the months-long transit, time spent on the Martian surface, and the route back to Earth. During this time, astronauts would be up to hundreds of millions of miles away from Earth, facing communication delays of up to 20 minutes each way. This means that even the simplest back and forth exchanges with mission control could take over half an hour. The practical implications of this delay are significant. Astronauts would need to develop the capacity to troubleshoot complex systems, navigate unforeseen crises, and make critical decisions with minimal external input. This level of autonomy demands rigorous training, but it also raises the psychological stakes in ways we have never encountered. The emotional dimension of this isolation cannot be overstated. On Earth, astronauts aboard the International Space Station have the comfort of being just a call or video chat away from family and loved ones. On Mars, such interactions may feel hollow and disconnected, as the long delays strip conversations of the natural flow and immediacy that help maintain emotional bonds. Over time, this could lead to heightened feelings of loneliness, stress, and detachment from the very people and environments they are striving to protect. To mitigate these challenges, space agencies like NASA are pioneering research into self-sufficient crew dynamics. This includes ensuring that astronauts are not only trained in technical and medical skills, but also prepared to support each other emotionally. Strategies such as fostering strong interpersonal relationships among crew members, creating vibrant routines to simulate life on Earth, and using advanced technologies like virtual reality to provide immersive, familiar experiences are all being explored. Additionally, efforts to improve communication strategies are underway, including pre-recorded messages, delayed video exchanges, and even the use of artificial intelligence to create simulated conversations that can help bridge the emotional gap. NASA is also focused on developing sustainable life support systems that allow astronauts to grow their own food, recycle water, and produce oxygen. These innovations aim to reduce reliance on resupply missions, fostering a sense of autonomy and security for the crew. However, despite these advancements, the reality remains that a mission to Mars represents a new frontier in isolation. The physical and psychological distance between astronauts and Earth will test the limits of human endurance and adaptability in ways that no previous mission ever has. As we strive to push the boundaries of exploration, the profound lessons learned from tackling the challenges of isolation on Mars will undoubtedly shape humanity's path toward even more distant destinations in the universe. As the next challenge unfolds, the exploration of uncharted territories in space presents risks that push the boundaries of our preparedness and imagination. Venturing into the unknown means facing environments we have never encountered, where the unexpected is not just a possibility but an inevitability. Take, for instance, the daunting task of navigating asteroid belts. These regions are not the dense, chaotic minefields often depicted in movies, but they still harbor a myriad of hazards. Even with careful planning and advanced tracking systems, spacecraft must account for the unpredictable trajectories of smaller debris, which could collide with devastating force. The margin for error is razor thin, and one miscalculation could prove catastrophic. Another layer of risk emerges when landing on unfamiliar planetary surfaces. Consider the Mars rover missions, which have offered groundbreaking insights into the red planet, but also highlighted the complexity of operating in alien terrains. The landing process itself is fraught with peril, as seen during the 7 minutes of terror, where the slightest malfunction in descent or landing sequences could result in the loss of years of effort and resources. Even after a successful landing, the challenges continue. Rovers have faced issues such as wheels becoming stuck in soft soil, unexpected slopes, or mechanical wear from harsh conditions. Now imagine these risks scaled up to human missions where the stakes are exponentially higher. Unforeseen obstacles, from hidden crevices to volatile weather patterns, could jeopardize both the mission and the crew's safety. Beyond mechanical and environmental concerns, there lies the overarching uncertainty of biological or chemical factors we have yet to discover. Subtle chemical reactions in unfamiliar atmospheres or exposure to unknown compounds beneath the surface could pose serious threats. While every precaution is taken, the truth is, we can only prepare for scenarios we can predict. The essence of exploring uncharted territories lies in embracing the unknown, but doing so demands resilience, flexibility, and an unwavering commitment to problem solving. Advances in artificial intelligence and machine learning are helping us anticipate and adapt to some of these challenges by enabling spacecraft to make split-second decisions and react to anomalies. However, technology alone cannot eliminate the risks inherent in these ventures. It is the human spirit of exploration, combined with meticulous preparation, that will guide humanity as we traverse these frontiers. As we reflect on the triumphs and setbacks of missions to Mars and beyond, each step into the unknown teaches us invaluable lessons, shaping the future of space exploration. Moving forward, these insights will be critical as we prepare for even more daunting challenges that lie beyond the horizon, where ethical dilemmas and the exploitation of extraterrestrial resources await careful scrutiny. Now turning to the ethical dilemmas tied to space exploration, we find ourselves at the intersection of progress and responsibility. As humanity looks toward harvesting resources from other planets, moons, and asteroids, there arises a critical question: do we have the right to exploit extraterrestrial environments? Advocates argue that utilizing resources beyond Earth could solve pressing challenges like energy shortages and raw material scarcity. For instance, asteroid mining has been proposed as a way to access rare metals that are essential for modern technology. However, this raises concerns about the environmental and ecological consequences of such actions. While planets and asteroids may seem lifeless to us, the potential existence of microbes or unknown ecosystems means that our interference could irreversibly alter or destroy these habitats. Furthermore, there is the moral consideration of whether these environments should be preserved for scientific study rather than being treated as commercial assets. Beyond resource exploitation, the moral debate also extends to the value of human life in the pursuit of exploration. Space missions, particularly those pushing the boundaries of our capabilities, come with significant risks to astronauts' lives. Is it ethical to send individuals into situations where the likelihood of survival could be uncertain? Proponents of exploration argue that risk is an inherent part of human progress and that the bravery of astronauts drives our collective understanding forward. Yet, others caution that we must weigh these risks carefully, ensuring that no life is considered expendable for the sake of ambition. These competing perspectives underline the need for clear ethical frameworks as we venture further into space. International cooperation will play a pivotal role in setting these standards. Treaties like the Outer Space Treaty emphasize the peaceful use of outer space and prohibit national claims of sovereignty over celestial bodies, but these agreements are only a starting point. As commercial and national interests grow, decisions about who can access resources, how they can be used, and who is responsible for potential damage will become increasingly complex. Balancing scientific curiosity, commercial ambition, and ethical integrity will require a global commitment to fairness and transparency. These challenges highlight not just the technical and physical hurdles of space exploration, but the profound moral questions that shape our role as stewards of the cosmos. Moving forward, considering how to balance our curiosity with responsibility will determine the ethical foundation on which the future of space exploration is built. With the next phase of the journey in sight, balancing our insatiable curiosity with the weight of responsibility becomes the cornerstone of ethical space exploration. As we push the boundaries of human knowledge, the frameworks we establish today will dictate not just how we explore, but who we become as a species. Ethical frameworks are not merely guidelines, they are the moral compass that helps navigate the uncharted waters of space exploration. Without these frameworks, there is a risk of repeating the mistakes of our own history, where unregulated resource harvesting and territorial disputes led to environmental degradation and conflicts on Earth. By learning from these lessons, we have an opportunity to take a more thoughtful and mature approach to exploring the cosmos. International cooperation is a beacon of hope in this endeavor. Agreements like the Outer Space Treaty represent humanity's collective aspiration for fairness and peace in space activities. But as more nations and private corporations enter the race, the framework must evolve to address emerging challenges. For example, how do we define accountability when a private company causes irreversible damage to a celestial body? Or who owns the data and resources collected from these explorations? Addressing these questions requires an inclusive approach, one that brings all stakeholders, from scientists and governments to corporations and the global public, to the table. Only through open dialogue and cooperation can we build policies that reflect the ethical principles of equity, transparency, and sustainability. The role of education and public awareness in shaping these frameworks is equally crucial. By fostering a culture of responsibility and curiosity, we can inspire future generations to explore space not just for profit or prestige, but for the betterment of humanity and the preservation of the cosmos. As global citizens, we must ask ourselves, what legacy do we wish to leave in the infinite expanse of space? The answer to this question lies in finding harmony between our desire to know and our duty to protect, ensuring that the pioneering spirit of today does not overshadow the ethical stewardship required for tomorrow. And as we move forward, understanding the complex and interconnected nature of universal exploration will define how we progress as both explorers and caretakers of a vast frontier unknown. As we draw this journey to a close, let us reflect on the 20 hidden dangers of space exploration that we have unraveled together. From the invisible threats of radiation exposure and unpredictable space weather, to the physical and psychological tolls of microgravity, isolation, and limited resources, each challenge underscores the immense complexity of venturing into the cosmos. We have explored the risks of equipment failure, fuel shortages, and space debris, as well as the ethical dilemmas of alien pathogens and human contamination of pristine celestial environments. Beyond these immediate dangers, we face profound questions about our ability to navigate unknown territories, balance curiosity with responsibility, and ensure international cooperation in this new frontier. These perils are not mere obstacles but vital reminders that scientific progress must be matched with foresight, innovation, and unity. Addressing these challenges is not just essential for the safety of current and future missions, but is also key to shaping the legacy we leave as a spacefaring species. So what do you think? Which of these risks surprised you the most, and how do you believe we can overcome them? Share your thoughts in the comments below. We'd love to hear your perspective. And if you enjoyed this journey into the mysteries and challenges of space exploration, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. Together, let's continue exploring the wonders and enigmas of the universe. Thank you for watching, and see you in the next adventure.